Hello, everyone. My name is Joel Palathinkal. I am one of the instructors at Product School. I'm really excited to talk to you today about quantum computing, the exciting applications that it has for industry and computing as we know it, and the opportunities for product managers to get involved. So let's get right into it. I'm going to share my screen and I'm going to go through my presentation. So let's kick it off. Quantum computing for product managers. Let's first talk about myself. I'd love to introduce myself. My name is Joel Palathinkal. I am the Chief Product Officer at Sutton Capital, and I'm also a Managing Director. We're a fintech investment company. We also do venture capital. Genesis Block Ventures, I'm also the Chief Product Officer and General Partner there. We're also an investment fund that focuses on various different types of investment applications and technology. In the past, I was a head of product at Northwestern Mutual, really running their digital innovation in fintech. And at FactSet, I was also their head of product, running their digital technology platform strategy. Previously, I did a stint in the media industry, so worked at NBCUniversal and CBS as a senior product manager. And I also worked for the Department of Defense, really building flight simulation technology as a project engineer. As far as my education, I was an electrical engineer, later studied finance at Cornell, and then got my PhD in modeling and simulation from the University of Central Florida. So quantum computing, it's not about if it's going to happen, it's when it happens. So it's already here, but there's going to be more advancements and it's going to be more mainstream adoption in the coming future. And I'm going to talk about how long I think it's going to take for it to be more involved in our lives. But first, I'm going to take a step back and give you guys a little bit of background. Then let's talk about the now, near, and far for quantum. And then finally, I'll wrap up with how quantum computing can be integrated in with the career of a product manager. So taking a step back, the first digital computer was created in 1945. That was the ENIAC computer. This marked a switch from mechanical to digital computing. This was Turing complete. That means it could recognize or decide other data manipulation rule sets. And the next leap in the coming decades will be truly from digital to completely quantum. But we're taking baby steps as we get there. So what makes quantum appealing is the use of quantum mechanics and properties to accelerate computational applications. Qubits are cooled subatomic particles like electrons of photons. Qubits need to be controlled in a quantum state, and classical computing won't go away anytime soon. That's the computing that we know today. And that's because it's the most economic solution right now. You don't have to worry about cooling technologies and maintaining the quantum state or stability with classical computing. So let's talk about classical computing. So today, the way that we know computing is in the format of zeros and ones. So your PC performs calculations using bits. They're units of information encoded electronically in either the off state, which is the zero, or the one, which is the one state. Which is the on state, which is the one state. So the traditional computer tries possible answers one by one until it finds the right one. And that process is just far too slow for such complex problems. Now, when we get into quantum, we call this the qubit. That's a quantum bit that can exist as a 0 or a 1 or both simultaneously. And that trait is known as superposition. Adding more qubits, therefore, increases the number of states that can be represented exponentially. And superposition, as you see here, is one of the properties that enables it to work faster by considering many possibilities at once, sorting through sets of probable outcomes that converge on the correct answer. So as you see here, you're almost like you're omniscient, thinking and doing at the same time in several different ways. Entanglement is really taking pairs of qubits that can be created in a single state. So when one is changed, the other one can predictably be changed. This exponentially increases computing power with this type of entanglement strategy. However, in classical computing, doubling the bits would only double the processing. So you're not going to get that exponential type of outcome that you would with entanglement. Quantum supremacy, we've read about this in the news. A quantum computer is able to perform a calculation that is impossible for a classical computer to compute. Google achieved this in 2019. It was one of the first instances which stirred controversy and really triggered the quantum race. There's also the concept of decoherence. These qubits are fragile to the environment, so noise and vibrations can impact the quantum state, and that causes decoherence. Scientists have to keep them cooled. However, there was a recent breakthrough in Australia where they found a way to still quantum compute 10 times in a warmer temperature. Photonic circuits are another solution that will hopefully get us to room temperature, and that's because it maintains the stability of the quantum bits. PSI Quantum is a really interesting startup that raised $150 million in funding. They use silicon photonics. Those are really particles of light, which are photons, and they use those photons to do quantum calculations. Those are known to be much more stable, and they maintain the quantum state for a longer time. So PSI Quantum, one thing that is really notable about them is they're aggressively aiming to have 1 million qubits within their quantum computations. That's a huge step function larger than the industry standard, where a typical quantum computer only has about 100. So a couple of these other existing technologies is the superconducting qubits. These are the most commonly used technology for quantum computing. It's really these devices that are small coils fabricated on chips that resemble those found in classical computers. And then there's these trapped ion qubits. They're the oldest qubit technology dating back to the 90s. Most prominent commercial users are really those atomic clocks using that trapped ion technology. So now let's talk about now, near, and far. So when it comes to now, there's the NISQ era. That's really when you're focusing on error mitigation. Broad quantum advantage, which is still around 10 years away. That's when you're getting to error correction and solving all the challenges that quantum has right now when it comes to stability and just errors and having a lot of noise in the calculations. So this is really when you're able to do near real-time risk assessment. This is really valuable to financial services firms, specifically quant hedge funds. But it's just not applicable now because of all the error that's still caused with the current state, and still for the next probably 3 to 5 years. And then really when we get to 20 years, that's when we get to full-scale fault tolerance. That's really when we're getting to the enterprise grade modular architecture, very mature frameworks and technology. And that really takes us to a 450 billion to 850 billion operating income with that type of complexity and technology. So diving a little deeper, this now sector, which is 3 to 5 years, NISQ, that's noisy intermediate scale quantum. It's allowing you to create useful discrete functions, but that still has large error rates. So accuracy will still be a large challenge, and error mitigation is still needed. So a couple applications that you can look at. One of them is combinatorial optimization. This is minimizing or maximizing an objective function, such as finding the most efficient allocation of resources or the shortest total distance among a set of points. So you can see this being a huge use case when you look at network optimization, when you look at mobility, airlines, taxis, Ubers, supply chain, logistics, and then on the financial side, portfolio optimization, right? So the quickest way to get to an outcome when you're doing some type of quant modeling, just the shortest path, that's where you're going to really use combinatorial optimization, using different combinations of strategies to get that outcome that's the quickest. Differential equations, that's going to be really helpful when it comes to fluid dynamics, simulations for automotive and aeronautical designs. Medical devices are going to be huge when you're looking at the flow of blood and modeling how the blood is going to flow. Molecular simulations for specialty materials design, drug discovery. That's really when you're going to be looking at differential equations. If any of you guys studied engineering, that's like calculus 4 pretty much, and I had to do that. So getting fond memories of all those 2-page long calculations. But anyways, a third application is using linear algebra, right? So machine learning tasks involving matrix diagonalization, risk management and quantitative finance, DNA resequencing. So when you're resequencing the genome, looking at genomics technology, marketing and customer segments could also be another one. So really looking at training models and machine learning, that goes back to linear algebra. Cryptography and computer security. The most common protocols today rely on infeasibility for classical computers for factoring the product of two large prime numbers. So that's really how cryptography works, factoring the product of two large prime numbers. So decryption and code breaking are going to be huge use cases. And I'm going to talk about this later, but a lot of those cryptography applications that we know today could become obsolete. So thinking about how quantum is going to transform that and be the next generation and possibly provide a better solution for what we have today could be the outcome when we look at quantum deeper. The next 10 years, this is when we get to broad quantum advantage. I call that near. And this is when we're going to see large improvements in velocity, price, and performance outputs. And we're going to overcome large hurdles when it comes to accuracy, consumption, dependability of quantum computing hardware. And then the FAR, that's really the full-scale fault tolerance. That's when I told you guys that we're going to have mature applications, frameworks, technologies, modular solutions. This will affect a broad array of industries and provide massive wealth and opportunity. This will aggressively accelerate drug discovery, algorithms in finance, and various other industries. This will also provide significant value creation in various industries as well, as I mentioned. This is an interesting chart that kind of visually depicts what I was talking about earlier. You can look to the far right, see the massive growth from each section of evolution as far as the operating income, right? You're looking at 2 to 5 billion, all the way up to 25 to 50 billion. So that's almost like a 5x multiple. And then going all the way up to 450 to 850 million. So that's a large multiple in growth as far as value creation. And then you can see as the step in different sectors change, and it makes sense to show that it's flat, especially in some of the sectors, because as you develop the technology and you have the foundation, you can easily jump to the next vertical. So a couple interesting quotes. Obviously, there's a lot of opportunity in materials design and drug discovery, because instead of running one model, you can run several millions of models at the same time and run several different scenarios at the same time simultaneously, which you currently can't do now in a binary world. Income gains from portfolio optimization have the opportunity to go up to 400 million in the next 3 to 5 years. And then just that whole holistic value creation of full-scale fault tolerance, that's what gets us to that operating income of large magnitudes. And then we see here just other views of how the industries are going to get impacted. So definitely in the near term, finance is a large use case, especially at the enterprise level. Large companies like JP Morgan are hiring the quantum computing scientists from Google and from IBM. So you're seeing a lot of these people leaving big tech companies and going to private equity, because that's where the applications and opportunities are. When you're a product manager, you may not have to develop the algorithms, but you're still going to need to figure out what problem are you trying to solve, who's the customer, who cares, why are you building it. So when you look at artificial intelligence, quantum computing allows to process various data points at the same time. So if you're working in AI now, if you're working at a company that uses models, really transforming your mindset to think in an omniscient way, where data points could be running simultaneously. They could be doing things at a much faster velocity, and just the paradigm is completely shifting. So changing your mindset to be able to think about those use cases and think about how the technology is really going to provide huge advantages to your customer, I think is going to be critical from the product manager standpoint. And then just the downstream impact is when you have that framework, the models are going to be trained much faster. So you need to make sure that you can keep up with that and be able to be supporting these AI-focused tech companies to develop not only the infrastructure, but also on the front end, a lot of the tools that you're going to be building are for developers. Um, as far as consumers, they're not really going to know what's going to be happening under the hood. They just want to open the app and see the client side experience and not really know a difference. They need to do one or two taps and complete the goal that they need to achieve. And everything else that's running under the hood, that's running better, faster, and cheaper, is all the secret sauce that you're doing behind the hood using quantum computing versus the traditional binary computing or just historical data that you're using to train models. And I would say when it comes to artificial intelligence, this is going to be critical and important in every industry, whether it's autonomous driving, whether it's healthcare tech, chemical simulations, drug discovery, material sciences, or even flight simulation. Just understanding modeling, simulation, and AI is going to help you just go deeper in these sectors and add a lot of value. Molecular modeling is also going to be another huge theme. Google has also been really involved in this, specifically for solar cells. How can you model out an ideal solar cell that's going to last longer? You might want millions and millions of data points of synthetic data, and you might want to test various different permutations of those solar cells to get the highest performing one. Fertilizer as well. You can model out various types of fertilizer before you actually manufacture it, using chemical compounds in a simulator before actually creating the real compounds or trying to find them or put together those different compounds. And then pharmaceuticals are all compounds as well, right? You're mixing 2 to 3 different types of chemicals. Some of those chemicals might have a reaction when you mix one unique chemical with another. So doing that in a safe environment where you can model that out before you actually create the drug is always great. So those are huge applications, huge markets. I talked about cryptography. So quantum truly could potentially make the current type of cryptography obsolete. So thinking about, as a product manager, how can you support this technology framework? And again, really empathize with the customer and build the right problem. You could build some type of cryptography solution that provides 10 solutions, but maybe your customer only needs 1 or 2. So this is going to be more of an important time to still continue to listen to your customers and build the right thing. Because if you don't, it could get down the rabbit hole of where a lot of people made mistakes when it comes to blockchain, right? People just are spinning up instances of a blockchain database when it's not really needed, when you can actually do the same thing with AWS. So as I've asked before with blockchain technologies, do you really need a blockchain? I'd ask you, do you really need quantum? And see what the true application is. And again, is it truly solving a problem? I talked about fintech earlier, just going 2 levels deeper. Quant arbitrage is going to have a great opportunity. So training these financial models, generating a large set of scenarios of outcomes based on a trade, whether you're long or short. What are 5 different outcomes that can happen? And can you spin those all out at the same time? And could it also give you recommendations that you didn't even think about in a unique way that typical historical data won't? I think that's the edge that quantum gives. Financial weather forecasting, so better climate models, detecting disaster predictions, detecting them better, more accurately, much more effectively, quicker. Those are things that are really going to transform the weather forecasting market. If there's startups that can do it better, faster, and cheaper than the incumbents, there's a huge transformational opportunity there. And then the best type of quantum computing is done right now with photons, so better stability. So there's opportunity to kind of innovate new types of particles, particles like ions, just more solutions to deliver these computations that you can run much faster, more effectively, but most importantly, maintain the quantum state and stay stable. And these new types of computational applications with ions could pair with other types of particles, or you might even, you know, discover new particles that you never knew of before. So investing in the R&D to still continue to innovate on that is a huge opportunity. And then just developing different types of simulations that use quantum computing and exploring new markets, exploring new opportunities. And as a product manager, again, you're always empathizing with the customer. So making sure that you're covering all of the problems. If you can't solve all of the problems now, put it in your backlog. And maybe as quantum evolves, maybe it will lend itself to support those use cases and workflows in the future. So super excited about the future of quantum, and I'm very happy that I was able to share this with you. So thank you for taking some time out to listen to me and hear some of this thought leadership. I am open to all of your comments. I'd love to co-author anything with you guys when it comes to quantum or just deep tech. Feel free to shoot me a note. It's just my first and last name at Gmail. So Joe Palathinkal at Gmail. I'm also on LinkedIn. So thank you so much and be well. And I wish you the best. Thank you.